All right, so this is 12.2. We're going to look at some techniques for evaluating limits when we can't just use direct substitution. So when that kind of fails out on us and we have to look at some other options. So we're going to talk about several different techniques in this day one. We're going to do the first three sections here of the notes. So I'm going to start with a warm-up question, something that we were doing before. So we're going to look at this example first, so if you can add that in there. So we're going to look at this limit. These are ones like we were doing yesterday in these polynomial rational functions. So we have a degree 2 on the top and a degree 1 on the bottom. So rational function. How we always started before is we were talking about what the domain was. So the domain for this is all reals. X can't be equal to 4 though. So that's where we're going to be discontinuous on our graph. The question is what kind of discontinuity is it? So we can definitely take a peek and take a look at the graph. So if you can take a moment and just go ahead and type that in, type in your equation so you can see what it looks like. All right, so taking a quick peek at the graph, it looks like that this is a degree 2 divided by a degree 1. Looks like a linear equation now. When we looked at those before, what kind of discontinuity do you think is happening at 4? Because that's definitely the place that we know it's an excluded value. Well, there's no asymptote there, so I am guessing that this is going to be just a point discontinuity. And if you remember how we did these before we talked about direct substitution, we just traced. So if I trace on my line here, my graph, as I get closer and closer to 4, it sure looks like my value is getting closer and closer to, I guess, 1 if I had to guess. If you go to your table, that was another way we tried to deal with these. If I try putting in 4, I know it's going to say error. I could pick numbers on either side, and we can also check. But I'm pretty confident it looks like it's approaching 1. If I try that direct substitution, though, that we did yesterday, and I put in 4, my issue is I get something that I can't really deal with. It's 0 on the bottom, but it's also 0 on top. So 0 over 0 is a really weird place to be. It's called indeterminate form. If something's indeterminate, that means you can't determine what's going on. We don't have enough information yet. We're going to have to do some other things. So when we look at a situation like this where we end up with 0 over 0 and we do direct substitution, we're going to have to do some other methods to help us figure out what that limit is. One of those methods could be what we just did. It could be looking at the graph, right, and doing a trace and trying to come up with the best approximation we have. Now, if that's not a whole number, though, it's going to be pretty hard to trace on the graph, right? We talked about the limitations of that. So let's see if we can figure out some other options. Remember, if it's a point discontinuity, we talked about this earlier, that's also called a hole on the graph. But there's this other great word that helps us remember what we're actually going to do. Starts with an R. The removable discontinuity. And what I mean by removable is that there must be a factor in common if I get this 0 over 0 that I can remove so I can actually evaluate the limit. So I'm going to take a look and see if I can factor this numerator. So x squared minus 7x plus 12 would be x minus 4x minus 3. And the cool thing about that is now I can remove the factor x minus 4 and I'm left with just x minus 3. Now I can actually evaluate the limit then, right? I remove the thing that was causing the issue, and my limit I can actually directly substitute into this expression, that 4, so I can see what happens as it gets closer and closer to 4. Sure looks like the limit to me is going to be 1, which is exactly what we were seeing on the graph. So we can use our knowledge of algebra, this idea of factoring, and remove those discontinuity places. So when I take a look here at kind of a strategy to talk about this, when you try to evaluate the limit of a rational function by direct substitution and you get this indeterminate form, 0 over 0, that you can really know from that the numerator and the denominator have a common factor. So the numerator and the denominator have a common factor. And so if they have a common factor, that means we should be able to factor and divide it out and then be able to evaluate the limit. So this is one of those removable discontinuities, being able to actually take out the thing that's causing us problems. So let's try one more though so we can deal with what that looks like. So the limit as x approaches 3, very similar kind of format. If I try to just plug in 3, just so we can look at that direct substitution idea from yesterday, what would happen? Well, in the denominator, it's for sure 0. In the numerator, 9 minus 24 plus 15, there's that indeterminate form. I can't tell enough information from that. So let's see if we can factor it, right, and simplify, because I know my domain is all reals except for 3, right? So I know that there's a discontinuity happening at x equals 3. The issue is, can I remove it? Is this one of these point discontinuities or holes? If it's not, then we're going to have some other issues we're going to have to talk about. But if it's removable, then I'm going to be able to evaluate that limit. So the whole idea is making sure we understand this idea of domain and what it's going to be able to look like for us when we find that limit. So let's see if we can factor and remove this discontinuity. So it looks like we have an x minus 5, x minus 3 over x minus 3, and sure enough, we can simplify that, right, and remove that discontinuity. Now our equation, x minus 5, I'm going to be able to evaluate that limit. So I can substitute in the value, and it sure looks like it's going towards -2. Now you can definitely go ahead and still graph these and trace and really see that connection between the algebra that we're doing and what the graph is telling us, which is always a good idea to kind of piece those things together. So this was definitely a point discontinuity happening here. It was removable, it was a hole, so the limit still exists. So even though the value of the function didn't exist, right, the value of the limit did. And we talked about that with rational functions before. So removable discontinuities are something that we can deal with when we get that indeterminate form. So it's a great way to be able to tell. We're going to take a look at another one. So I'm going to have you add this one. So I wanted you to see one that had a higher degree on the bottom than it did on the top, so we can kind of compare and contrast that a little bit. So we're going to do the limit as x approaches 7 of x minus 7 over that cubic on the bottom. So if we tried direct substitution and we just plugged in the numbers, we'd have, not 0. We'd have 7 minus 7 on the top, 7 cubed minus 7 times 7 squared plus 7 times 7 minus 49. And if you take a second to do that arithmetic, you end up with, guess what? 0 over 0. Not super helpful, right? Because that indeterminate form. But what that does tell me is that there must be a common factor that I can take out. And if I can take out that common factor, I'm going to be able to calculate the limit. So let's take a look and see how we might want to do that. So at the bottom, take a look. It has 4 terms. If we're going to try to factor that, do you remember how to factor something with 4 terms? That is factoring by grouping. All right, so the first two we pull out x squared, which would leave us an x minus 7. And then the second two we pull out a 7. That would leave us with an x minus 7. And then we can pull out that common factor. So we've got x minus 7 over x squared plus 7, and then x minus 7. So I'm going to be able to simplify that fraction. I'm going to move this so I can move this down. We'll show the graph then as well. So I can remove that factor of x minus 7, and I'm left with 1 over x squared plus 7. Now, when I think about, okay, can I do direct substitution now? Well, sure, because as it approaches 7, take a look at this denominator. Can that ever even be 0? We're never going to have an issue down there, right? Because anything squared is positive plus 7. Think about what the graph of this would be. It would be a parabola with the vertex moved up 7. Never even crosses the x-axis. There are no real solutions to this. So the only excluded value, if I think about the domain of this function, the only issue that I had was at 7. So now that I've removed that discontinuity, I can calculate the limit. So it would be 1 over 7 squared plus 7, which would be 1 over 56. Now that would be a really hard number to trace on your calculator, right? To try to figure it out by graphing and tracing. What I did for you here is I graphed the function. And you can go ahead and graph it too, type it in. And then I zoomed in. I showed you what my window was here so you can see. I zoomed in right just around 7. So I went from 6.5 to 7.5. And you can see very clearly the hole, that was that removable discontinuity, but the limit definitely exists. As I close in on 7 from each side, the graph itself is closing in on that open spot, that 156. So we definitely have a limit. The limit exists. It was just a removable discontinuity. So when we take a look at what that means for us, we just have to see if we can factor. So algebraic things that we can factor and remove, we can calculate the limit. All right, let's talk about some other techniques. Sometimes you can't factor. And when we talk about other types of equations and formats, sometimes we get stuck and we can't factor. So there's another technique that's just kind of cool where you rationalize. You change the format by rationalizing. And we've done this before. We've rationalized before. We're just going to use it in a little bit different context. So another way to find the limits of some functions, not all obviously, is called rationalizing technique. So the rationalizing technique means you rationalize something to help you get it into a different form. So rationalizing means we're going to multiply by whatever we need to sort of undo or get rid of whatever thing we're trying to get rid of, usually a radical. So I'm going to go ahead and just write down the different options that we could be running into here if we might need to rationalize. So one is if we have radicals, whether it's in the first position or the second. So you could have a whole number plus or minus a radical, or you could have the radical plus or minus the whole number. It doesn't matter which the radicals first or second. When we rationalize in that situation, we multiply by the conjugate. So we're going to be actually usually rationalizing a numerator when we're doing this to try to change things out, but it could be rationalizing a denominator as well. So what it basically means is this: you multiply both the top and the bottom, so the numerator and the denominator, by the conjugate of the numerator. And it might seem weird to do that by the numerator, but it's important to recognize that which part you're trying to change. So if we're trying to change the format of the numerator, then we multiply by the conjugate of the numerator. And see if you remember what conjugate is. So if we have an expression, numerator, there we go, I can spell. If we have an expression like a plus b, the conjugate is a minus b, so like the same expression with the opposite sign. So we're going to try rationalizing as a means to try to change the format so we can actually evaluate the limit. So let's show you one that could be solved in that fashion. So let's take a peek. So find the limit. All right, so here's the expression. Now, when you look at this, this does not look classically polynomial or rational function, right? Because we don't have whole number powers. We got just a disaster going on as far as that goes. We got a square root function. If we try direct substitution, so I'm just going to try that, look what you end up with. We end up with 1 minus 1 over 0. Square root of 1 is 1. So you end up with 0 over 0. What that's telling me, that's indeterminate form. There must be a way to get a common factor out of this. Sure doesn't look like it right now, but if you get 0 over 0, you must be able to reduce that fraction. Let's take a look at the graph. So if you can go ahead and get that typed in, pause the video, go ahead and get that typed in. I'm going to show you my version then. All right, so my version, again, I can show you the window that I used. I zoomed way in. You wouldn't have to. You can start off at the negative 10 to 10, but that's the window that I used. What we're trying to see is as x approaches 0, so as the x values get closer and closer to 0, what is this graph getting closer and closer to? There is an open circle there, so we definitely have a point discontinuity at x equals 0. We know what the domain of our function is, right? The domain of this is all reals, but x can't be 0. So of course, I can't be just plugging in 0 in that denominator. But how would I be able to show it algebraically and not just say, hey, well, I think it looks like it's going here, but I don't really have a method to show that. So we know that this is going to be a point discontinuity. I can see it on the graph, but I want to be able to show that algebraically and be able to evaluate the limit. So how can we do that? So let's see if we can use that rationalizing technique. So I'm going to try rationalizing this to show where that's approaching. So I'm going to multiply both the top and the bottom by the conjugate of the numerator. So I'm just going to recopy my expression here. What would the conjugate of the numerator be? Well, it's going to be the same binomial, but with the opposite sign. So 1 plus the square root of 1 minus x. So 1 plus the square root of 1 minus x. All right, well, in the numerator, that just means doing some distributive property. So first, outside, inside, last. So 1 minus, and some people won't even put these two middle terms because they know what's going to happen to them, but I will. So we will minus that radical plus that radical. Now last, this is what I want to talk about. You've got a minus, right, times a plus, so that's going to be minus. The radical times itself will be 1 minus x. Super important that we put that in parentheses because we're subtracting the whole thing. On the bottom, I'm just going to go ahead and leave it right now as a multiplication. Let's simplify the numerator. It looks like our radicals will add to 0. We've got a 1 minus 1. That's going to add to 0. And then we've got a minus a negative x plus x. All right, now take a look. This is so cool, this rationalizing technique. Now watch what happens. Don't you have a common factor in the top and the bottom? All right, so I have a factor of x up top, and in the bottom, I'm left with 1 over 1 plus that radical. Now, think about evaluating that limit. So can I actually directly substitute a 0 now? You sure can. We've got 1 over 1 plus 1 minus 0 under the radical. So the square root of 1 is 1. 1 plus 1 is 2. Sure looks to me like that limit should be a half. I'm going to go back up to the picture here to my graph and see if that seems reasonable. If you look at your scale, look where it's crossing. This sure looks like it could be crossing at a half. So when I think about what I would have maybe guessed by tracing, I can definitely see by doing the rationalizing. So if you get that indeterminate form, that 0 over 0, we need to take a look at how we might be able to factor that. And rationalizing might be a way to get there. So that's another option. So it's not applicable all the time, but it's a great option when you see that sort of format, that conjugate idea. All right, so let's talk about another technique. Sometimes none of that works. You can't do anything algebraically, and then we can use some technology. So these are kind of the catch-all for some of the situations that maybe you can't solve algebraically. So to find limits of non-algebraic functions, we really are going to just approximate, which is kind of my red flag for I'm probably just going to use my calculator here, using some form of technology. So we're going to approximate what those limits might be. We've already done a lot of this. We're just going to make it a little bit more precise today. So think back to what we did initially to calculate a limit. We numerically would look at a table, right? And we would just sort of scroll in and get closer and closer and closer to the value, see if we can approximate. We also graphed, right? So graphically, we made the graph and then we traced, which also gives us a pretty good indication of where things might be. But sometimes that's hard to kind of nail down an actual number, especially if they're decimals. So think about this. Remember we made the table, right? And we were picking numbers that were on either side of whatever the value was. So say our C value, whatever that might be, 2, 7, whatever, we were picking numbers on either side to try. Things like 0.001 and then maybe negative 0.001, whatever that might be. And we were trying to close in on what the C value was. Well, think about where that value would be located. It's right in the middle of the two values that we're picking on either side, right? So if we're trying to calculate a number for this, what if we know the value of the function on either side of it? How would you find the number in the middle? Well, that's just an average, isn't it? Right? So if we average the two values that are equal distant on either side, we should be able to come up with the number in the middle, which would be our limit. So that's exactly what we're going to be trying to do, making that numerical approach that we did the other day just a little bit more precise. So we're going to take an average. So we're going to average the y coordinates of 2 points that are equal distance from that C value. So we're going to find the average of the y coordinates of 2 points that are equal distance from that C value. And if we can do that, then we can just make that a little bit more of a precise calculation. So we're going to try that on a couple and just see how that might look when we're trying to do our solving. So let's take a peek at one. Some of these functions you're going to see a lot in calculus, and that's why I want to talk about them right now. So the limit as x approaches 0 of e to the x minus 1 over x. Definitely not a polynomial. We are not in polynomial land anymore here. So we definitely need to think about some other options. So we can't put in 0. We know the domain of this function, all reals. X can't be 0, so we know we're in trouble there. If we try to do direct substitution, we're going to get anything to the 0 power is 1, 1 minus 1, 0, 0 over 0. We're not going to be able to calculate it directly. We have that indeterminate form, though, so we know we probably can do something. Go ahead and take a moment to type this equation in. So please go ahead and type in e to the x minus 1 over x. So you can pause the video and go ahead and type it in. I zoomed in quite a bit, so I did like 0 to 1 and -1 to 1. Go ahead and do the -10 to 10 to start with. That's fine. You'll see that exponential kind of graph. It certainly looks like as we close in on 0 that we are closing in on an open circle here, that I should be able to calculate that. If I just trace, it's going to be kind of hard to maybe see, but maybe we can actually tell where that is. So if you can trace on your calculator and see what that looks like, maybe we can get at least a rough estimate before we start doing our calculation. So I'm going to go ahead and get that pulled up, and then we can take a look at tracing. All right, so here's our graph. I'm going to go ahead and trace and I'm going to get a little bit further back here so we can come back at it because it's undefined at 0. We know that. If I come back and watch as x gets closer and closer to 0, what the y is doing, if you had to guess a whole number as it gets close, sure looks like it's pretty close to 1 to me. So if I take a look at my picture, the zoomed in version going up to 2 there, that 1 in the middle, kind of makes sense. So I think it might be 1, but let's see if we can make this a little bit more precise. So I'm going to go to my table and clear out these old ones here. Just for kicks and giggles, if I type in 0, yeah, it says error. What if I pick up number equal distant on either side? So I'm going to go back to our philosophy before where we were doing like the 1/100th. What if we do that? What if we do positive 1/100 or 1/1000, sorry, and negative 1/1000th, trying to get to where that 0 would be in the middle. So let's try those points that are equal distant on either side. So I'm going to go ahead and enter those in. And then 0.001. What if I average those? Okay, so that would be the point, technically that would be right in the middle of it, and 0's right in the middle of those two values. So we had for the first one 0.9995, and then we had 1.0005. I think a really good approximation then would be finding the average of those two values, because that should give us the number right in the middle. So if they're equal distant for the x's, should be equal distant for the y's as well. So let's average those two and divide by 2. And if you average those, guess what you get? 1, which is certainly something that we could justify by looking at the graph as well. So I think this is very similar to what we did initially when we talked about limits, but it's a little bit more, I guess, precise when we try to talk about those numbers. Let's try one more of those and make sure we're okay. So let's do a cosine graph. This is a great one to talk about. We do a lot of trig functions, obviously, in calculus that we're trying to prepare for. Limit as x approaches 0. Well, same issue we've had on all of these. We can't put in 0. Direct substitution, 1 minus cosine of 0 over 0. Cosine of 0 is 1. We're going to get that 0 over 0. Go ahead and graph so you can take a look at what the graph would look like. So go ahead, take a second, pause the video so you can graph. All right, so here's the graph. If I look at a smaller version, more zoomed in, just right around the origin, so I kind of zoomed in right on this little area right there, it sure looks like we got that open circle. As I get closer and closer to 0, it definitely looks like it's closing in right at 0. So if I had to guess by just looking at the graph, I'd probably say 0, but we're going to do the same sort of thing. I know it's an error there. Let's pick a point equal distant on either side. I think for this one, we can even just do 1/100th. And let's see what happens. So we're going to go to our table, and we're going to put in those values on either side. So I still have it on ask in my table, so I know I have the same kind of situation going on here. Sometimes it's nice to kind of have to mess around a little bit, but find numbers that aren't too small, but they just have to be equal distant. So 1/100th, and on either side, looks like we get a negative 0.005 and a positive 0.005. So how about we average, right, to find the point that's right in the middle? So the limit would be the average of those two values. And if we average those, we are definitely going to get 0. So it's just a nice technique to kind of formalize, I guess, our guessing and checking. Our approximation we can be pretty confident in if we take a point that's equal distant on either side to be able to find that. So we looked at 3 different methods today for dealing with functions that maybe have harder limits to calculate. So one of them was the dividing out technique, so dividing out common factors if you have that indeterminate form, 0 over 0. Another one we talked about was rationalizing the numerator, so you can see if you can divide out a common factor, so getting it into a different form to be able to solve. And the third one was approximating, right? So if we can't do algebraic means because they're not polynomials, things like cosine, e to the x, is there a way then that we could use that average, right, in our table, so a little bit more precise way to approximate a limit?